Hi! Now we are leaving mechanics and crash course physics and looking at fluids. But we will see that many of the principles and notions from mechanics, such as force and momentum, and energy also, apply just as well to fluids. Let's start with atmospheric pressure. This is caused by the numerous collisions of molecules of air surrounding us from all directions. The contributions from the left and right actually cancel each other out, but there's a net force due to the gravitational force caused by the column of air directly above us. This column of air has a weight of about 10 tons per square meter. Multiply this by the gravitational acceleration and you get the standard pressure of about 100,000 Newton per square meter or 100,000 Pascal. Now, this seems like an enormous force pressing down on us, but it is not the same as if say a hydraulic press were pressing down on us, because this pressure is imparted by a fluid, by air, which we can easily displace with our bodies, and so this immense force is actually dissipated in a sense all around us. If we were surrounded by air in the absence of gravitation, then all the little collisions from all directions would cancel each other out and we would sense no net pressure and the air would just dissipate away, since it is not bound by any gravitational force to the Earth. A curious little invention that was presented in this episode was based on Pascal's principle. It seems almost impossible that we can just multiply a force by any factor that we want in order to lift heavy loads. It seems to contradict the principle of conservation of energy and of momentum. Here I just want to point out that this is actually not the case and how to reconcile this with energy and momentum conservation. If we displace the left piston by a certain distance, then since the fluid is incompressible, we can only move the right piston by a much shorter distance. Since force times distance traveled is the change in energy, this change in energy that we impart on the left comes out exactly in the same amount on the right. So conservation of energy is not violated here. This bears actually a lot of similarity to the principle of the lever, with which we can also multiply the force applied by any multiple that we want, but of course the distance traveled by this force is much shorter. What about momentum? Since force is just change in momentum, it would appear that we put in more momentum into this fluid than we actually get out on the right. And that is absolutely true. This extra momentum comes where else? From the Earth, and if this were actually mounted on a movable ground, we would actually also see that this ground gets a recoil to the left. The barometer is also a weird little device. What hasn't been mentioned in the episode is that the little bubble on top of the mercury is actually a vacuum. It is created by submerging the column completely into the mercury in a horizontal position and then lifting it out. Then the sheer proper weight of the mercury sucks out this vacuum from the upper end of the column. What might be a more proper description of this situation is that the atmospheric pressure, the air surrounding this, is just not heavy enough to lift the mercury in the column up to the top. The 76 centimeters of mercury that it can lift are equal in weight per area than the surrounding column of air. If we were to perform the same experiment with water, the column of water that could be lifted by the atmospheric pressure would be more than 10 meters high. Now on to buoyancy. Buoyancy is also a very non-intuitive kind of force, and it's worthwhile to look at the microscopic origin of it. Buoyancy is caused by, again, collisions of molecules onto the submerged body. This could be in a fluid that is either a liquid, such as water, or even air. Yes, we're experiencing buoyancy from our surrounding air as well, which makes us a little lighter. The origin of buoyancy is that the little collisions of the molecules onto the submerged body do not cancel each other out completely. The net collisions from the lower part are a teeny tiny bit larger than the collisions from the top. Now, why is that? That is because the density of molecules increases with decreasing height due to gravity, so that the particles on the lower part of the body are ever more slightly more packed together than the particles on the top. They are not faster, which would mean a higher temperature, but more packed together, so they experience more collisions at the same kind of velocity. So the net impact force created from the bottom is larger than the net impact force from the top, so the overall force difference creates this upward directed force of buoyancy. A neat little application of this is to look at an iceberg. There are two forces acting on this iceberg: the force of gravity and buoyancy, which is only caused by the submerged part of the iceberg. As both forces cancel each other out in equilibrium, the ratio of the two volumes, submerged part versus the whole volume, is equal to the inverse ratio of the densities, so density of ice divided by the density of seawater in this case, if you want to look up the numbers, and we get a ratio of around 87%, so that about 87% of the iceberg is submerged underwater. So that was the Crash Course Physics Nitpicks for this episode. Don't forget to subscribe and follow me on Twitter. See you next time.